So in last lecture, we have discussed about the multiplexers. Now in today's class, we are going to discuss about demultiplexers. So as it is clear from the name, demultiplexer, that is, it is the reverse process of a multiplexing. Again, a demultiplexer is also a type of switch. In case of the multiplexer, there was n number of inputs and one number of output, and the reverse process is done with the help of demultiplexer. So as far as the definition is concerned, a demultiplexer or demux basically reverses the multiplexing function. It takes data from one line and distributes them to a given number of output lines. For this reason, the demultiplexer is also known as a data distributor. So in case of a multiplexer, there was many number of inputs and the output was single, that is, we can say parallel to serial converter. And in case of demultiplexer, there is a single input and many number of outputs, and we may say it is a serial to parallel converter. So when we need to transmit our data serially, one by one, then we use multiplexer at the transmitter end. So the n number of inputs will be converted into a single bit output, and at the receiver end again we use a demultiplexer which converts a single input into the many number of outputs. So as far as the block is concerned, we can say single data input line, some select lines, and always select lines are in the ratio as it was in case of the multiplexers, and several output lines. And the relation between select line and the output line is like 2 raised to power m equals to n, where n is the data output line and m is the number of select lines. So here we can see the functional diagram of demultiplexer. It has a single input. Again, it will act as a switch, and depending upon the value of the input select line, the input will be provided at the particular output, and which output is connected to the input, that depends upon the select line. So here you can see it is a switch. Now whatever is the value of the select line, its select line will select that switch will be on at which output line. Now let us consider a 1:2 multiplexer, demultiplexer. We have a select line S0. As the output is 2, so single select line is used because 2 raised to power 1 equals to 2. So the relation is always holds when we are selecting a demultiplexer with particular number of input select lines. So whenever S is 0, the output will be connected to the first input D. The first output will be connected to the input, and the next will be other output will be 0. And when select line is 1, then the second output will be selected. So here we can find out we have used another input enable, that is E. E stands for whenever E is 1, that the chip will or the IC will work. Otherwise, whenever E is 0, all outputs will be 0. So whenever E is 0, we have used AND gates. Whenever E is 0, then the output of the both AND gate will be 0. That means we say that there is no valid input. The chip is not selected. Whenever E is 1, then the output will depends upon the value of S0. If S0 is 0, that means here is 1, here is D, then the Y0 will be D, but here it will be connected to 0, so output will be 0 because S0 is fed to the second AND gate. Whenever S0 is 1, then this output of this NOT gate will be 0. That means the output of the first AND gate will be 0, and the output of second AND gate will be, here is E1, S0 is 1, then the output will be equals to D. So this is the way how a demultiplexer is connected with the or constructed with the help of the AND gates. Similarly, 1:4 demultiplexer, for the 4 output, we need 2 select lines because 2 raised to power 2 equals to 4. So here we have used 2 select lines, S0 and S1. Whenever S0 S1 is 0 0, then the output will be at the first input, at the first output, rest are 0. When it is 0 1, output will be input will be at the second output. Whenever S0 S1 is 1 0, it output will be input will be at the third output, and whenever the value is 1 1, then the input will be at the fourth output. So in the same way we can construct the circuit diagram. Here it is the input is connected to all AND gates, and depending upon the value of S0 and S1, the output will be selected, that which input is connected to the output. So here you can see that depending upon the value of S0 and S1, input will appear at the particular output. Now comes the last topic of unit 1, that is programmable logic devices, and in short we say it's PLDs. So there will be one question from PLDs in your examination, in sessional as well as the main examination, and the question length will be it will be asked at least in 7.5 marks, or it may be 12 marks. So let us discuss first that what the PLD means. There are two types of memories that are used in a digital system. Let us talk about the memories you have very well known. First is the random access memory, RAM, which performs both write and read operations. And another one is read-only memory, that is ROM, performs only read operation. The read-only memory is a programmable logic device. Other such units are the programmable logic array, that is PLA. Programmable logic array is PLA. Programmable array logic is PAL. Field programmable gate array, FPGA. And as far as your course is concerned, we are going to discuss ROM, RAM, PLA and PAL. The FPGA is not a part of your syllabus, but now let us discuss about the array logic, what the array means. So a typical programmable logic device may have hundreds to millions of gates interconnected through hundreds to thousands of internal paths. So these are the arrays like matrix. In order to show the internal logic diagram in a concise form, it is necessary to employ a special gate symbology applicable to array logic. So what we see, conventional method is A. If we say that we have n input OR gate, so it will look like this. So here it is a 4 input OR gate. So we have 4 inputs, 1 output. But in case of the array logic symbol, we show like this. So we say that this is a 4 input OR gate. So whenever you are using an array or you are designing an array, the circuit diagram will be like this. So single input, and we have a cross matrix. So this is your conventional symbol for combinational logic diagram. Whenever we are talking about the array logic, so we'll use such type of symbol. Now let's first discuss the read-only memory. As I have told you, in case of when we are designing decoder and when we have implemented Boolean function with the help of decoder and the OR gate, and that combination is known as ROM. So a block diagram of ROM is shown below in the next slide. It consists of k address inputs and n data output. The number of words in a ROM is determined from the fact that k address input lines are needed to specify 2 raised to the power k words. So where we have a decoder, and with n number of input, the output of the decoder will be 2 raised to the power k. So each output is known as a word. So this is the block diagram. We have k number of address line. We have n number of output lines or data lines. So what we do, we use k is to 2 raised power k. K is to 2 raised power k. That is, if we are using like 5 is to 32, 4 is to 16 decoder at the input line, and we have a register where we store the data. So we'll discuss in detail how does it how it look like. Suppose we are using a 5 is to 32 decoder. So this is your address line. Address line is 5 and it has 32. 2 raised power 5 is 32. 32 distinct addresses. So these are known as, these are the addresses and these are the words. So here we get 1, 2, 3, 4, 5, 6, 7, 8. Then the memory will be 5 is to 32 decoder and the each word is of 8 bit. So these are the bits. So each output of decoder represents a memory address. 0 to 32, 0 to 31, that is total 32 are the memory addresses. Each OR gate must be considered as having 32 inputs. So here we can see that each OR gate has 32 inputs. So we have shown in the last to last slide that how to symbolize array. So this is an array. An array has 32 input. Each array has 32 input. And total word, the size of the memory is A0 to A7. These are the word size, that is 8 bit. A 2 raised power k into n ROM will have an internal case 2 raised power k decoder. So this is the size of the decoder, and the memory will be 2 raised power k and n. So here we say 32 by 8 bit. This will be the size 32 by 8. 32 to 2 raised power is 32, and the size of the word is 8 bit. So we say 32 by 8 bit ROM. So this is how a ROM is constructed. Now a programmable connection between two lines is logically equivalent to a switch that can be altered to either be closed or open. Intersections between two lines is sometimes called a cross point. So here we can see these are called the cross points. So whenever it is open, the value of this cross point is 0. Whenever it is short, the value of the cross point will be 1. So suppose we have a ROM truth table, that is we have used a partial ROM truth table, and the value of A7 is 10110100. These are the 32. This is a word size. So the word has 10110110, and these are a array. The value of the array, where there is a 1, there is a cross. Wherever there is a 0, there is a open circuit. So in the table, the whatever number of figure and table I am using here, these all are your figure and table number of your textbook, that is Morris Mano and Switching Theory and Logic Design. So all table number and the figure number I am using from your book. So when there is a 0, there is no connection. When there is a 1, there is a connection. Suppose address 3, we have 10110010 is the permanent storage using fuse link. So here we see if we have to store this word 10110010. So what we do, we put a cross mark 1 0, again a cross mark, that is 1, again a cross mark 1 0 0, that is open circuit, then 1 a cross mark and a 0. So here X means a connection. Where there is a cross mark, there is a connection. So address line 3, address line 3, that is 0 1 2 3, that is the fourth address, has a storage of 10110010. So this is the type, and the programming of the ROM is done at the time of the manufacturing. Whenever a system is designed, whatever is the permanent data or your boot data in your system, that is stored in a read-only memory. Now, how to implement a combination circuit, combination logic in the ROM? The internal operation of a ROM can be interpreted in two ways. First, a memory unit that contains a fixed pattern of the stored word. Second, implements a combinational circuit. Now in figure 7.11 may be considered as a combinational circuit with 8 outputs, each being a function of 5 inputs. So whatever is this circuit, so we have 8 outputs. These are the 8 outputs, and the input is 5 bit. So A7 has the input A0, I4, I3, I2, I1, and I0, and it is the summation, that is min terms 0 to 29, 0, 2, 3, 29. So here we have seen min terms are 0, next is 2, 1, 0, 0, 0, 1, 0 is 2, 1, 1 is 3, and 1, 1, 1, 0, 1 is 29. So this is the way how it is represented. Now design, consider an example, design a combinational circuit using a ROM. The circuit accepts a 3-bit number and generates an output binary number equal to square of the input number. So the question is clear, input is 3 and the output is square of the input. So first derive the truth table. It is table 7.4 in your book. So the input are, I have taken here, sorry it is wrongly written, A2, A1, A0. When it is 0, the square of the 0 will be 0. When input is 1, square of the 1 is 1. When the input is 2, 0, 1, 0, then the square must, 2 square of 2 is 4. So we have 1, 0, 0. When the input is 3, square should be 9, and we have represented 9 in such a way. When input is 4, then 16 is the output. For the 5, it is 25. For 6, it is 36. And for 7, it is 49. So here we require a 6-bit of output to represent 49, because 5 bits are required to represent up to 31. So up to 64 we require 6 bits. So this is the truth table, and how to derive the truth table, that is determined in that is already given in the question. And the question specification says that it must have 3 inputs and the output is square of the input. So we have to construct it. Again, I have redrawn the table. A2, A1, A0 are the input, and I have taken 1, 2, 3, 4 outputs here, because as you see that B1 is permanently 0 and B0 is equals to A0. You can see the value after comparing. B0 is equals to A0, or whatever. If you cannot derive the direct relation, you can solve the K-map for here you have to solve 6 K-maps, one for B0, B1, B2, B3, B4 and B5, like this. So I have removed B0 and B1 and I have constructed the table like this. It will be a 8:4 row, because with 3 input there will be decoder, 3:8 decoder. So the 8 outputs, and we have the room like this. Programming is first is B0 is A0, B1 is 0, B2 that will always be connected directly, and it will be done with the help of the decoder. All min terms will be defined by the decoder. So here is the way how to design or how to construct a combinational circuit with the help of the decoder, or with the help of the ROM. You first have to directly draw. You directly draw the truth table and just implement it with the help of decoder and a OR gate. So the next is types of ROM. I think we'll stop today's lecture here, and we'll start from the here onwards the type of ROM, and in the next lecture we are going to discuss ROM, RAM, PLA and PAL. So if you have any doubts, then you can